So I'll get started here. Let me begin with a word of prayer. Excuse me. I'll start. Dear Father, we thank you for this day. Again, I thank you for the students. Just ask you to bless our work today. Help us to glorify you, what we do, and understand a little bit more about your creation, Lord. In your name I pray, Lord Jesus. Amen. So I have tried to tell you guys sort of a big picture of some of the story of physics, and so we talked about special relativity and general relativity, right? So just to give a brief timeline here. So 1860s or so, we had electromagnetism, right? So Maxwell's equations pretty much cap that off, right? And then in 1905, you have special relativity. Which is sometimes abbreviated SR. This was Einstein. And then in about 1916 or so, you had what's called general relativity, or GR, as it's known. And again, this was Einstein. Although, truth be told, it's not just Einstein that had his hand in that. It really was, in some sense, gifted to Einstein that the calculus of curved space had been worked out by mathematicians already. So he had some toys to play with just sitting there. And a well-known mathematician of the time named Hilbert helped him kind of put things together in part. But Hilbert didn't ask for any credit. He did Einstein a pretty big favor in that he helped him out. Didn't really require his name to be on the theory or anything, because it was, after all, physics. As I mentioned last time, in 1918 or so, in the midst of World War I, Schwarzschild found this so-called Schwarzschild solution, which is the analog of, so you know how we solved the problem of, like, in Physics 1 we look at like the moon going around the Earth, or the sun going, or the Earth going around the sun. So these, and to a good approximation, we think of those as being like circular orbits, right? So that sort of maximally symmetric spherical gravity problem, that's the one we study in Physics 1, right? Well, Schwarzschild solved that problem for general relativity through a relatively benign modification of the argument that you see to solve that problem in like junior level physics. Hey, I wonder, maybe perhaps Dr. Budares will cover that next year. I hope he does. It's called the central force problem. We can solve the two-body problem. If you have two bodies that are interacting through a central force, variational calculus and formal classical mechanics allows a solution, in I think in general. Then when you get to the three-body problem, that you cannot solve in general. But anyway, so that's the situation. Now, quantum mechanics came on the scene. So obviously electromagnetism is its own thing. That itself was a synthesis, right? Because before Maxwell's equations came along, we had partial understanding that electricity and magnetism were linked, but that cemented the synthesis of electricity and magnetism. Then special relativity it's consistent logically with E&M. So like special relativity is already allowing for electromagnetism, but it does require modification of mechanics. I hope I convinced you that it's kind of weird, like what it says about velocity addition, the way acceleration transforms, things like that are really surprising. General relativity is even more sort of mind-bending, right? You're saying that gravity itself is a consequence of the curvature of space and time. It's hard. It takes a minute to really understand that. Like I had a class. I had two classes in general relativity, and in my first class we had a final exam, and like one of the problems on the final exam was just to work out, G, 9.8 meters per second squared. Like how does that work out from the equations of general relativity? And it took a lot of work to figure that out. I mean, like, it was a significant amount of work on my part to figure it out. And but it was, you know, that for me, this general relativity is what sparked in part my interest in mathematics, because in order to understand general relativity, I had to understand the calculus of curved spaces, all right, manifold theory and so forth. But once I understood general relativity, all of a sudden I realized that there was more that I needed to understand past that. And so quantum mechanics, and I'm not sure what the exact time to put here is, like, I would say 1900-ish, quantum mechanics. That's not really quite the case. I mean, I think probably more properly speaking, you maybe say 1925 or 1926, and I forget which one came first or second, but yeah, Schrodinger, which I can't spell. Schrodinger, I'm misspelling it, and there's one of them in there somewhere. And Heisenberg, I'm better on that one. Watch me misspell it too. But Schrodinger and Heisenberg and others, they laid down the logical foundation of quantum mechanics. And but there were other little bits and pieces that led to this point. So before we had the formal theory of quantum mechanics, we had isolated instances of its necessity. Like the photoelectric effect, like I told you guys last time, was found by Einstein in 1905. That's an inherently quantum mechanical thing. The black body radiation, the way black body radiation works, that was the discovery of Max Planck in that's early, like 1910-ish or something like that. So there's just this collection of little experiments here and there at the dawn of the 20th century, which were pointing towards some inadequacy in physics that ultimately led, in its culmination, to the discovery of quantum mechanics. Right? So quantum mechanics, this basically describes, this is physics for very small scales, is one way to look at it. All right? So if you get to really, really tiny things, we have to use quantum mechanics, all right? And essentially, quantum mechanics makes contact with regular mechanics in the large. So if you have very large objects, the quantum mechanical effects are in some sense like unobservable. They're boring because they just become regular classical mechanics, because, you know, you take this average, and there's something called Ehrenfest's theorem, which basically says that on the average, quantum mechanics works back to regular mechanics. Quantum mechanics, also sometimes called wave mechanics, or it's born from wave mechanics, because these guys, Schrodinger, Heisenberg, the others, von Neumann played a significant role here. All these guys were deeply educated in formal classical mechanics, where they studied the properties of waves far more deeply than we do anymore. All right, so quantum mechanics came from their understanding of wave physics, and ultimately sort of thinking of particles as both a particle and a wave. It had this dual nature. You're probably more familiar with that idea from light, right? Like light is both a wave and a particle. It has wave-like nature, it has particle-like nature. So which one is it? Well, it's both. So I made a handout for you guys. So it's just one page. But this has a bunch of spelling for things I'll be saying today. So quantum mechanics, 1925, 26, something like that. And so, like, there are problems quantum mechanics solved pretty much almost immediately from its inception. One of the problems it solved is what we call chemistry. Pretty much all of chemistry is simply applied quantum mechanics. Very little of it. I don't know if there's any of it that isn't just quantum mechanics, really. So, like, have you guys ever heard of spectroscopy? Do you know what spectroscopy is? Sort of every material, if you burn it and you look at the light that it makes, it has a character, sort of a DNA, a footprint, a signature set of frequencies it releases in the light that it emits as it burns. It's so-called spectrum. So spectroscopy allows you to look at the specific frequencies and, you know, the energy of photons that's released from burning certain elements, and so you can kind of tell which kind of element you're looking at from that. And so anyway, early quantum mechanics was certainly verified and justified because of its success in explaining things like why the if you've had a chemistry class, they talk about, you know, like electrons being happy. You know what I'm talking about? If they're in the right place, they're happy, they stay there. They're in their, like the valence, was it valence electron? Man, it's been forever to say that class. But all of these different orbitals, right? The orbitals of the hydrogen atom or hydrogen-like atoms, all of these things can actually be derived from solving Schrödinger's equation for that atom. And it's just a matter of basically special functions like the second course in differential equations can derive all that thing. All of the spheric, all of the wave functions you've heard about in chemistry, these things can be derived from like the second course in differential equations. So there's obviously something like real about quantum mechanics in that it explains a lot of chemistry. It predicts what's possible and what's not possible in terms of chemical interactions. So chemistry, so I would say kind of just, you know, a 30,000 foot view of what I'm giving you kind of a 30,000 foot view. But this stuff eventually more or less tells you about electronic interactions. Chemistry. And so what I'm talking about is EV, like electron volt kind of stuff. So like, you know, the difference in energy between different orbitals of an atom. We're talking about electron volts. That's the kind of energies involved, right? If you look at the handout I just gave you, let's see if we can find any energies on here. Oh man, I meant to make this double-sided. What happened? Oh, this is just me. You guys got a single-sided one. Confused myself. Oh man, rats. I got no numbers. I chose poorly. But if you could see, if you could see the numbers, the energy is characteristic of nuclear interactions. So like, oh man. So after this, in about 20 to 1950-ish, something like this, you know, nuclear physics. Can't spell. Nuclear physics. We're talking MeV. That's million electron volts. All right. So chemistry sort of concerns one energy level. God in his providence has made physics so that it's segmented into different stories, typically separated by like 3 orders of magnitude. So you can completely understand chemistry and all the while be totally ignorant of the substructure of the nucleus, right? And then later, once you get better toys, you can start studying what's the structure of the nucleus, right? And that's the genesis of nuclear physics, which used to be called high energy physics until we got to high energy physics. So like what is quote unquote high energy physics is a moving target. But so here you had discovery of things like the pi mesons, properties of the neutron and the proton, how they interact, all that. These things came into light. And about this same time, quantum mechanics got an upgrade. So quantum mechanics, it's physics for very small scales for particles, whatever that means. But it's also what's called semi-classical. Originally, quantum mechanics is semi-classical, meaning that it's kind of a mix of a classical theory, which is what we studied in Physics 1, right? Which classical theory, the features of a classical theory is it involves the continuum. There's no discretization. Quantum mechanics, on the other hand, involves discrete quanta. You know, there's discrete steps typically involved. But past quantum mechanics, we got to what's called quantum field theory. So quantum field theory, of which there's several different varieties, You have your QED, you have your QCD, and, oh man, wait a minute, QFD, and QCD, I think? Yeah, I don't know. So QED is the first one. This was discovered around World War II in the early 40s, like 1945-ish, something like that. You have like Feynman and also Schwinger. A Japanese dude I can't spell, Tamanga or something like that. I don't know. So I'm misspelling that horribly, but there's a Japanese physicist. So this was one of my token evidence. So I took a class. I still talk about this class because it was just so incredible. Ever you take a class in college that's just so incredibly stupid? You'll be talking about how stupid it is the rest of your life. Maybe you've had a class like that. Hopefully not here. But I had a class like that. It was called The Rise of Modern Science. And in that class, among other things, it was claimed that the actual results in science, the results in physics, are a societal product. Not just that society can, turn on or off the presence, I believe this is true. I think a society can become so corrupt and so devoid of truth that you can stop finding new physics because you're no longer interested in the search for truth, right? Like this happens. You can have a very evil leader who just tries to kill all the scientists because he views them with jealousy or something, right? These kinds of things have happened in history. But if the switch is on for intellectual inquiry, if you're looking to find truth, I believe in the existence of objective reality because I think that's how God, in His providence, has created the world that we live in. So I find this proposition in my Rise of Modern Science class that the actual results in physics are shaped by society. Like, to me, this was just insane. And my example was that Feynman and Schwinger, US scientists, found quantum field theory, and so did this Japanese scientist in World War II. I mean, if you can't have two more separated societies than that, I don't know what can you have. But of course, this is like shooting fish in a barrel, because it's all the time the case that very disparate cultures that are both studying science find the same results, right? Because it's not a consequence of, how Marxist your country is or something, what kind of physics you find, right? It's completely detached. Anyway, so this quantum electrodynamics, it's I don't know how to explain it briefly, but in short, it's the quantum mechanics of fields. This is much more difficult than quantum mechanics that we apply in like the solving. Like, everybody here could take one more class in differential equations, and you also could solve. It would take you a week or so, but you could work out the solutions that describe the orbitals in chemistry. All right, you could do that. It's not that hard. This stuff, much worse. And there are unresolved. There are parts of this which have been done mathematically correctly, but there are other parts which are super sketchy. All right, so they're going off of very shaky physical reasoning that's somewhat guided by intuition, somewhat guided by experiment. There's something they do called renormalization. In the process of renormalization, you go from a classical theory to a quantized theory. And in this process, there's certain divergences, infinities in the theory. What do you do when you find a divergence in calculus 2? You say, my job is done here. It diverges, right? Game over. What physicists do when they find a divergence is they lump it into a known physical quantity that they can measure, and they just call it renormalization. So like it's not quite that, but it's not far. Like, there's something very sketchy with how renormalization is done. I think we understand more about it than we did like when I was in school, I'm sure. But I think there's like tons of mathematics that has not been settled here. We're well past the mathematics and what we're doing physically. And so, so anyway, QFD, I'm trying to say quantum flavor dynamics, or I'm thinking electroweak theory. And this is quantum chromodynamics. And so that's the physics of like quarks, right? Physics of quarks and such. All right. So, man, let me take a step back here. So on your page, if you look at it, right, we got. Let's see, which side are you guys looking at? Let's look at the side with it's on the top. It says the 4 fundamental interactions of nature. So it's got some things that are broke down in terms of. So first of all, you got gravitation, all right, and then you got electroweak, and then you've got the strong force. So the electroweak force includes both electromagnetism and the weak force. The weak force is responsible for things like radioactive decay. All right. For example, if you had a neutron and it was sitting out in free space, after 11 minutes it decays into something called a proton, which you've heard of, and I think something called an electron neutrino. Maybe an electron. I think maybe I'm trying to remember. Man, this is not good. I need to take nuclear physics again, obviously. But so shame on me for not knowing what the free neutron decays into. We can figure it out. You have a neutron, it decays into a proton. So something has to happen here, right? This has 0 charge. This has charge positive 1 electron volt. So I'm pretty sure there's also an electron involved. So this has charge plus an electron. This has minus the charge of the electron, right? This is plus 1.602 times 10 to the minus 19th, minus 1.602 times 10 to the minus 19th coulombs. But then I believe that there's also, for reasons I can't explain, an electron neutrino that has to be part of this. I believe. So a free neutron will decay into a proton, an electron, and I think an electron neutrino. If I'm wrong, I'm sure we can find the correction in the comments to this video. I mean, I have hope. But my point is that this is a signature weak interaction. The weak force is what causes radioactive decay. Now, you're probably not used to thinking of radioactive decay for anything except for like radioactive stuff, right? But neutrons, their happy place is in nucleuses. In the nucleus, right? So neutrons are bound together with protons in the nucleus. They can stay like that for forever, pretty much, all right? There is a whole story there about how you can combine nucleuses together, and you know, what's possible there is very interesting. I think, you know, you can fuse very light nuclei together to make more heavy nuclei, and you can gain, they're like lower energy states, right? So like, as you do that, you have nuclear fusion, which you can get energy from. And then on the other hand, you can take higher, more weighty nuclei, and you can break them up into pieces, and that's called fission, right? So nuclear weapons are based on both of these ideas. And of course, one of the sort of holy grails of the snake oil salesman in physics is like this cold fusion business. I don't even know about the cold fusion, whatever. I got nothing to say about that. Let me not say anything. But so there are 4 forces. Gravity, I talked to you guys already about a fair amount. Electromagnetism, that's most of what we've done this semester, right? The weak nuclear force is radioactive decay. So like I told you, the electric and the weak force, they're if you could turn up the temperature in this room enough and get to a high energy state, we think that the electric and the weak forces are part of a unified electroweak force. When I say we, I mean current physicists. So then the strong force has 2 different aspects. The one is the fundamental, the other is the residual. The fundamental is what the quantum chromodynamics talks about, all right? There you have gluons. Gluons are the force-carrying particles for the strong force. The gluons are what glue the quarks together, basically. So I mean, it's very silly terminology, but that's what it is. So phenomenologically, the strong force, it is the force which binds the nucleus together through nuclear interactions, all right? So everything I'm describing to you today so far, these four forces I'm talking about, this is high energy, this is the so-called standard model of physics as we understand it, all right? This has been the story in physics since, I don't know, this electroweak story I'm telling you about, electroweak symmetry breaking, this is like early 1970s, something like that. You know, the stuff about quantum chromodynamics, that's a little bit like later in the 70s, maybe early 80s. By the time I was a child, the standard model had been pretty much stated and put into place more or less as it still is today. There's a little bit of funny business going on with different species of neutrinos. Like there's still some questions there that are unresolved, I believe. There's the giant gaping question of what on earth dark matter is and dark energy is. You can find people saying anything you want about those things if you look online long enough. Because basically what that means is we don't really understand astrophysical scale phenomena. Like if we look at the rotation of galaxies around, like, you know, rotation of solar systems around the galactic center, the rotation is not explained by the gravitational objects which we can see. So it's like, where is the rotation coming from? How do you explain the dynamics? People are like, well, there must be something that we don't know about, and we'll just call it dark energy or dark matter. And so they can repair the fact that observations plainly state that the theories that they have are wrong. So, you know, what does that mean? I don't know. I think there's something very wrong with astrophysics as it's currently understood. I personally think that, you know, God gave us Genesis as he did for a reason, and I think that it means what it says. And as we observe things, we'll be driven to the Genesis account. It's just a matter of understanding. So I'm not really bothered at all by quote-unquote Big Bang cosmology or anything like that. Okay, so where was I? So quantum mechanics led to quantum field theory, and this led to the standard model. Basically, the standard model is a mixture of quantum mechanics, right? Quantum mechanics and electromagnetism to describe most of the particles. But there's also gravity, right? And these are they're just sitting together, and they're together form like the quantum mechanical theories, namely the electroweak theory and the strong theory. These are quantum mechanical theories. Gravitation is not. Gravitation has fundamental ideas in it which are just strictly speaking incompatible with quantum mechanics. The notion, if you listen to people who know more than I do talk about it, it usually, in some sense or another, comes back to the issue of the vacuum. Basic bedrock idea in quantum mechanics is that there's something called the vacuum. And the vacuum has this sea of particle antiparticles and the so-called Dirac sea. But it's kind of like a universal reference frame in some sense. And that just goes against relativity, roughly. I think if you can look up videos recently made by Sir Roger Penrose, I think it's Sir Roger, yeah, Sir Roger Penrose. He has a lot to say about our current understanding of quantum mechanics. Basically, he just doesn't believe that we're quite right. And he has some very powerful examples to explain why he thinks it's wrong. But so some of the issues in terms of our like philosophy of quantum mechanics, but really the question with quantum mechanics that's most unanswered is what exactly is the meaning of observation? What's the meaning of wave function, so-called wave function collapse? We don't really understand that. Excuse me. All right, so all of this to say, this is the standard model, 4 forces, and you have these, you know, particles, electrons, things you haven't heard of as much, like neutrinos, protons, neutrons, quarks at the base of everything. We think that so-called hadronic matter is made from quarks. So like a neutron and a proton are made from 3 quarks. But it's kind of a funny thing. You can't ever see the quarks individually. They've got like fractional charge, which is super weird. So one of the major things that was recently discovered is the so-called Higgs boson. So that kind of fits into this story. The Higgs boson is part of the Standard Model. It has to do with how the electroweak symmetry is broken. In the process of the electroweak symmetry breaking, as the temperature decreases and basically the universe freezes into place in some sense, in that freezing, this Higgs boson process ends up giving the force-carrying particles of the weak force mass, and yet the photon is massless. All right. So before the symmetry breaking, I think they're all massless, and then in the process of the symmetry breaking, Higgs had this explanation for how the photon, like the quanta of light, could stay massless, and yet the W plus minus and Z, the bosons, could become massive, which is why radioactive decay is very short range. It's not it's very, very short range. So anyway, this was very theoretical. Like, this Higgs boson has only been discovered a couple years ago, right? But with the discovery of the Higgs boson, maybe 5 years ago now, I think, that pretty much completes the story of the Standard Model. Like, it's kind of disappointing. It's like, well, where's the new physics? Like, what's past what we know? Well, we're not really sure. Like I said, the dark energy, the dark matter thing, that says there's something really wrong with astrophysics, I think. But, yeah. So, in the backdrop of all this, in about the early 1970s, people have been interested, of course. So this is a story of reduction, and as you combine things, oftentimes we've been able to take two smaller things and make them into one thing. Like electricity and magnetism come together to make electromagnetism, and then the weak force and the weak force and the electric force come together to make the electroweak force. So naturally, it's a tendency of physicists to try to just make everything the same thing. All right. So, what do you want to do next? Maybe combine gravity with these other things, right? A so-called grand unified theory. So people have been trying to find a universal theory of everything that lumps all these things together as one sort of monolithic whole for a long time now. And one of the things that happened in that pursuit was people started proving theorems about what couldn't be done. And one of those theorems is the so-called Coleman-Mandula theorem. That's not on your page. Let me find the spelling. I got the Wikipedia article right here. So, oh man, I thought I printed that out. Where is it? It's hiding from me. Well, that's annoying. I must have accidentally, oh, there it is. So, Coleman, I don't know why I'm spelling this for you guys. Nothing really matters to you. But once I start doing something, I have to finish it. The Coleman-Mandula theorem. Let's see if I can find a quick sentence to read about what it says. During the 1960s, a set of theorems investigating how internal symmetries can be combined with space-time symmetries were proved, the most general being the Coleman-Mandula theorem. It showed that a Lie group symmetry of an interacting theory must necessarily be the direct product of the Poincare group with some internal, compact internal group. So basically it linked future symmetry groups for grand unified theories with the Poincare group. What's the Poincare group? The Poincare group is a 10-dimensional group that has space-time translations. So you have like time translations, space translations. It also has like rotations and also boost. So it's basically a combination of Lorentz transformations and space-time translations. It's a 10-dimensional Lie group. And because of the structure of quantum mechanics, Coleman and Mandula proved that pretty much these hypothetical generalizations of current physics are very tightly controlled. They have to be connected to the Poincare group. But their assumptions involved thinking just in terms of what are called Lie algebras. So a Lie algebra involves a commutator bracket. So it's like, well, quantum mechanics is built mostly from commutator brackets, all right? But it turns out that you can also, if you're willing to think about it a little bit more esoterically, you can you can avoid the arguments of Coleman and Mandula by thinking about not just commutators, but also what are called anti-commutators. So this is kind of dumb, but commutators like this. All right, anti-commutator is like this. Seems kind of dumb, but allowing for this kind of thing, it circumvented the argument of the Coleman-Mandula thing. And people in the early 1970s discovered extensions, possible extensions of the Poincare group to ultimately what's called supersymmetry. So the Poincare group got extended to what's called the super Poincare group, although there's not one of those, so it's kind of, it's not a singular thing. So we added what's called supersymmetry. So supersymmetry is often abbreviated by SUSY, like that. Supersymmetry is a hypothetical symmetry. We don't yet know whether or not supersymmetry is real. All right, so it's something that has beautiful theoretical aspects to it, but we don't know if it's real or not. But if there is supersymmetry, it does some really weird things. It connects things like electrons to things like photons. It connects things with different spin. So the spin of a particle it describes how it interacts with the magnetic field in a very particular way. If you look at the handout I gave you guys, I have included for your amusement on the bottom of the second page a table from the Wikipedia article on the MSSM. What is the MSSM, you wonder? It is the minimally supersymmetric standard model, which is to say it is the standard model which I've been trying to describe to you as briefly as I can in the last half hour. It's the standard model paired with supersymmetry in the most tame way possible, like the least amount of supersymmetry you could put into it, let's say, the minimal supersymmetric standard model. And so what happens is, because you have supersymmetry, for every particle you get a super partner. So corresponding to quarks you get squarks. Corresponding to leptons you get sleptons. Corresponding to the W boson you get a wino. For the B boson you get a bino. From the gluon you get a gluino. From the Higgs boson you get a Higgsino. These people. But these people are taken very seriously. These people are taken very, very seriously. These people get billions of dollars to build things. You know, like, it's serious business, theoretical physics. I mean, I love it. But this is all hypothetical. So let me show you something, just for fun. So this is my my thesis. So my thesis, roughly speaking, was about studying properties of something called superspace. Superspace is the natural playground on which to study supersymmetry. You can realize the super Poincare algebra in terms of derivations on superspace. They look like this. So these are derivatives that are easy enough to think you understand, but the devil's in the details. So like, this is a derivative with respect to an anti-commuting coordinate. So what that means is like theta 1 times theta 2 is equal to minus theta 2 times theta 1. That's kind of weird, right? This, on the other hand, is a commuting coordinate. Those you know, all right? So the thetas are these new quote-unquote fermionic directions. The x's are, well, space-time, or time-space if you like. And what's really beautiful, I'll show you. All this doesn't matter to us too much. But the these W's, all right, these are called superfields, and these superfields contain in them the Faraday tensor, among other things, if I remember right. But it's more than just that. Let me get further here. I'll show you. So like, this is the so-called action. So these little stupid W's here, inside those expressions are contained not like a whole bunch of different fields all at once. So a single oh man, here I got some more understandable equations over here actually. All right, so here's a typical superfield. A superfield is a function on superspace. And in this one superfield, you have, let's see here, 1, 2, 3, 7, 8. You have 8 bosonic degrees of freedom. So these would be like spin 1 or spin 0 type fields. But then everything that's married to a fermion, these are so-called Weil spinners, or maybe I should say Weil spinners. And there you've got 2 there, 2 plus 2, plus 2 plus 2. What's 2 plus 2 plus 2 plus 2? That's 8. How many did I say? So there are 8 bosonic degrees of freedom. There are 8 fermionic degrees of freedom. So when you have supersymmetry, there's a natural like pairing of bosons and fermions. And writing things in a superfield automatically implements the supersymmetry. Here's the Poincare algebra I was just talking about. And excuse me. So this was the these are the supersymmetry generators, the Q's. So like, this is momentum. So basically you have the anti-commutator of supersymmetry generator in itself is equal to momentum. So this is why people will say sometimes like supersymmetry is like the square root of momentum, because it's kind of like you square the momentum and you get to supersymmetry. But anyway, just to let you know where this story goes, there are the relations. These are the defining relations for the super Poincare algebra. The n equals 1. Okay, n equals 1 just means one supersymmetry generator. You can add up to 8 of them. You can either have 1, 2, 4, or 8, as it turns out. I've only really ever studied n equals 1 supersymmetry carefully. I had some friends who, in the same time I just barely understood 1, she had gotten all the way up through like n equals 4. I was like, whoa, I am not cut out for this. These people are crazy. But anyway, so this stuff is just the regular Poincare algebra. But then here's how the supersymmetry interacts with momentum and with itself. So altogether, this defines the super Poincare algebra. So all this stuff is at the base of what's called string theory. So string theory is usually connected to supersymmetry, but they're not the same thing at all. Supersymmetry is very, very nice. Do you guys know you guys have calculus too, right? What are the nicest kinds of series? What's that? What's that?
Telescoping.
Telescoping. Yeah, I think that's right. And what usually happens with telescoping is you got plus minus, right? So that's how supersymmetry is. The bosons get like a plus, the fermions get a minus. If you got supersymmetry, when you have infinite sums, there's like a natural telescoping. It just, and so anyway, that's all I got to say today. But maybe I'll tell you more Friday, or maybe we'll just not have class Friday. What do you guys think? What's that? The fantastic part was me talking more about theoretical physics, right? Yeah. Or the not having class part. Which one was it? All right. Like, I'm not playing this mind game. All right.